Can everybody hear me? Yeah. So this is about DWARF, and the room has been emptied a lot for some reason, I don't know.
Is there anything wrong with the table?
Not that I know of. Well, maybe a little bit, but not much. Okay, so who knows about dwarf pieces already? Oh, at least some people. So one of the you can hear. So one of the goals of this talk is, of course, to explain a little bit about dwarf pieces, so everybody who knows them already may be a little bit bored, but I cannot help with that because it's really necessary. So I'm just jumping right in. DWARF has a concept of so-called composite location descriptions, and such a composite location description is a special location description for describing the location of a variable, right? Like other location descriptions. And a composite location description consists of one or more pieces, right? And each piece has a simple location description and a composite operation. And there are two such composition operations, namely the piece and the bit piece operation, right? They exist for a long time already, but they have not been started using at the time, at least not very much, at the time they were invented, because the compilers didn't optimize that well at that time. But now we are seeing more and more use of these operations by the compilers, so they have become more important. So let me quickly explain why pieces are needed at all. So one thing, of course, is the compiler optimization that, for example, spreads around things within a struct, right? When you have a struct and the compiler decides that one field in the struct is used particularly frequently in a hot loop or something, then this thing in the struct might be allocated in a register. And then some other pieces in the struct might not be needed at all. They will maybe not be represented at all, or they are only represented at certain times in the program, things like that, right? And then reconstructing the whole structure is basically just a composition of individual things, right? That's the piece operations. Well, that's what pieces means. So the same applies for bit fields, and that's why we need also a bit piece operation. Right? It's not sufficient to be able to compose pieces of full bytes. We also need pieces that are just sub-bytes, right? Another example is that an array may be spread across vector registers. That's another type of optimization, different one, right? Where maybe an array of whatever character array is spread across two vector registers or something. Then you would have also two pieces of this array and represent it that way. Another possible optimization might be to optimize out high order bits in a general purpose register, so not represent them in the register itself to avoid sign extension. I don't actually know whether the compilers do that right now. Another reason, apart from compiler optimization, to represent pieces or represent multi-piece composite locations is that some objects might be split naturally. For example, a long double value might be distributed across two floating point registers on some architectures, right? Some architectures express it like that. And then the hardware can really deal with that data and really do arithmetics within these two registers. Or another example is that some ABIs pass short, small structures also in registers, and even if 2 registers would be needed for that, right? And then basically the structure is composed of these 2 registers. It needs to be pieced together like that. So these are some reasons for pieces. So right now they already appear very frequently in optimized code anyway. And so what can a piece be taken from? Of course, a simple location. And these are basically the types of simple locations that we can use for that. So register, memory, a dwarf stack value. So it can also be something that we have computed from some other stuff, right? And an immediate value, which is basically a constant, so a literal. Or it could be empty, which means that this piece is optimized out. Then I have an example here. This is now a little cut off, but well. So you have this structure here, and the first element of the structure is a character, which means, or in this case, in this example, the compiler decided to represent this, to not represent this at all, but the compiler knows that in this point in the program, this character has the value 5. Yeah, then this can be expressed by this small dwarf code up there, literal 5, then take the stack value and then take a piece of 1 byte of this. After that we have 3 bytes alignment gap. So we express it by just a piece operation without anything in front of it, which means that this alignment gap is not there. There's just optimized out stuff. And then the next object would be an integer, and the compiler decided to put that into register 4, whatever register 4 is on this architecture. It's not a real example here. So this can be expressed by this code, and so on, right? It's not very difficult. The last example here with the short might be a little bit interesting because I use a bit piece here. You cannot see the parameters to that bit piece, but basically the bit piece parameter, the first parameter is the size, and the second parameter is the offset. Okay, the size would in this case be 16, and the offset 32. Okay.
So is it really actually possible for them both to be in the reg 4?
Yes. Well, in theory, yes.
Did you intend to write that, or is that?
Yeah.
Oh, okay.
I hope that somebody will jump at this, which you did. Yeah, right. Yeah, I mean, they don't overlap, so.
Okay.
Yeah, the integer is 4 bytes long and it's right aligned,
Yeah.
and the short is 2 bytes long and is left from that.
Okay.
In the same register. Yeah. Theoretically possible, I don't know
Yeah, maybe. Yeah,
if the compiler would really.
It is actually possible.
Yeah. It's possible that compilers might do this. Yeah. I haven't seen it consciously yet, but maybe. Now, another interesting question is, because we just talked about the short living in this, the short value living in this general purpose register at some point in the register. But at what point in the register, right? So this is the topic of piece placement. The placement of pieces is defined in the standard very vaguely, I would say. So this is the text from the standard here. If the piece is located in a register, but does not occupy the entire register. The placement of the piece within that register is defined by the ABI. So this is for byte pieces. And for bit pieces, the definition is a bit different. It says that the offset is from the least significant bit end of the register. Whatever that means. And these two don't agree. So I don't know what really is going on here.
Did you ask?
Yes.
Did you get a meaningful response?
No. I mean, the discussion went on for many weeks,
Yeah.
with many emails being exchanged and with no result.
So what do compilers do? Do they at least agree? Or
No.
Didn't the authors of the specification have a rationale for this?
I haven't seen the rationale. I have asked for it.
Yes.
Yeah. I don't think they have it still.
Insane.
Maybe they still have it, but I don't think so. It's pretty old, right? I mean, the dwarf pieces themselves are pretty old, and then there was a refactoring for the bit piece stuff, but even for that, I'm not sure anybody still really knows the rationale for that. Anyway, for memory pieces and implicit values and stack values, there's also a definition. It's even a bit different now here. Of course, for memory, the situation is different because what I expect a piece from memory to look like is, of course, that we always start from the address that we have given, not backwards, but right, always on the positive side of that address. That's my expectation. I mean, I think everybody else expects it like that also. The compilers certainly do, I think. But for implicit values and stack values, it's not that clear. I mean, for implicit values, my preference would be to treat it exactly the same as with memory, because implicit values look like memory, right? But that's also not what the standard says right now. As you can see. Whatever. I'm just showing you this because that's the only information we have about this, and it's a bit inconsistent. The implicit piece placement is also something that is not really defined by the standard. The standard doesn't even say that this is defined by the ABI. The standard just says nothing about this. Namely, if you don't use a piece operation, but just take a location and use this location for a type that is smaller than the location itself, right? Like when you have a register, but you only use 16 bits of that register. Which 16 bits are you using now, right? It's not obvious in some cases. If you take a short from a general purpose register, then it's pretty obvious that you probably want the least significant bits of the general purpose register. If you take a character array of 3 bytes, then it's a bit less obvious now. So I don't really know. And you can also look at this with other objects, like with stack values and with vector registers and with floating point registers. In all of these cases, it's not completely clear how the placement looks like, but there is at least in many of these cases an implementation in GCC already that does something. It's not necessarily true that it agrees with itself in all cases. And not with GDB also sometimes. Okay, whatever. One question that I had when looking at this was, if this is the case and we can just take a location and use a smaller piece of that location just implicitly, then what happens if we suffix an actual piece of operation after that? is that a no-op then? It's also not obvious, and I think most people think that it might be, but there are actually counterexamples for that. For example, let's look at Intel's 80-bit floating point registers. When storing them in memory, there are actually 128 bits. You can take, and implicitly, you usually take a 128-bit piece of that 80-bit register, which is actually too large, right? What happens now? So, yeah. So there are some things that are not completely clarified yet, at least. Now let's look at some stuff that should be more obvious. The composition of pieces. If you have multiple pieces and you piece them together, it's obvious how to do that, right? Yeah, if they are byte aligned, at least my feeling is that this is mostly obvious, because what you probably just do is you look at the in-memory representation of your value, and then you just add up the bytes at the end, right? You just put them at the end. But when it's bit aligned, then only bit aligned, yeah, so you have 2 bits. You need to append them now to your already existing pieces. Where do you append these 2 bits now? That's a bit less obvious. There are basically some assumptions that I would state about this. Namely, that if you do that, then no byte alignment gaps result out of such an appending bits operation. And also the next piece starts at the same byte or directly after the last byte of the previous piece. And the last byte only if not a single bit doesn't fit in this byte anymore, right? And within a byte, we use the ABI's bit allocation order. What that means is basically just this, right? If you write such a struct, then you know the bit allocation order of your ABI. It's obvious, right? Or is it? So what does it look like? I mean, on little endian platforms, at least on Intel platforms, it's pretty easy. The bit 0 is the least significant bit, right? And bit 7 is the most significant bit. On big endian platforms, it's usually exactly the other way around. And there might be platforms which do something completely different. I don't even know. Okay, so now that we somewhat understand where pieces come from and how we compose them into a composite thing, how do we actually use that in GDB, for example? We use that of course, by reading from such a thing and writing into such a thing, right? And what we actually read and write may not be the whole value, but just part of the value, because of struct members, right? We want to write to a struct member or read from a struct member, and the struct is itself composed of multiple pieces, and we apply this read or write operation to some of the pieces or whatever, right? The value also doesn't need to be, the value that we read or write doesn't need to be byte aligned, because bit fields, right? It also can spread multiple pieces when we want to write a substruct or whatever larger thing from a struct. And also doesn't need to be piece aligned. That's interesting, because if we have a union and one part of the union is the one that has been optimized by the compiler to load stuff into registers and things like these. But the other variant of the union looks completely different and is not aligned with the values that are allocated into registers and things like these. But in GDB we want to look at this now, or read this, or write this. Then we would like to be able to ignore the piece alignment in the one variant and just do the right thing, right? Whatever would happen in the real system as well. So what this means is we need a general bitwise copying function. Yeah. So everybody understand what that implies? A general bitwise copying function really copies a number of bits, any number of bits, an odd number can be, from an odd number, an odd bit offset, whatever, to another odd bit offset, right? So sounds pretty easy. But, well, no, it's not. And maybe because of the problems that we have actually seen in GDB, maybe that's one of the reasons that the vagueness in the standard has persisted for so long, because nothing of this has ever worked correctly. It's mostly completely broken up to last summer or something. So this list of fixes that has been applied to GDB is from 2016 and 17. Most of the fixes were done last summer in one large patch set where the whole piece handling logic was basically rewritten. So just an example, the copy bitwise function was almost correct. It just sometimes corrupted bits. Yeah. Yeah. This happened on little and big endian systems. So whenever, basically whenever we really needed to do odd bits copying, then it was broken, more or less. Also, when writing pieced values, there's a size capping logic, right, where we determine when does our value that we talked about, the sub value, right, this value here, when does that stop? And that value was also broken. It just calculated the wrong size, right? And then also on big endian systems, the dwarf stack value pieces were taken from the wrong end. So as soon as you actually needed something that was smaller than a stack value from the stack, it didn't work. You usually got zeros. This third problem caused many fails in the GCC test suite. Many hundred fails in the GCC test suite, which were ignored basically for many years. In the GCC test suite. We didn't have any tests in GDB for that. That's also one of the things that has been fixed. We now have test cases for all of these problems. Then the value parents offset basically means if you have a substructure in a structure, then you have a parent, right? And there's some internal GDB logic that deals with this, with the offset within the larger thing. And this offset was just ignored. So if you actually dealt with a substructure and a member of that, then the offset calculation was completely wrong. Then there was another copy-paste error in the size calculation, which I don't explain now. The transfer size is interesting. If you write a pieced value, then you have to check. Then there was an optimization, basically, that checked whether we can copy the stuff byte-wise. And if everything is byte-aligned, then we can do this. But this check did not check for the size. It only checked for whether we start at a byte offset, right? But if the size is not byte aligned, then this was also broken. So what else? Memory pieces had the wrong buffer offset. Yeah. So as soon as you needed an offset into a memory piece, it was also broken. Then the bit fields is an interesting thing. If you assigned a value into a bit field from an integer from GDB, right? If you said a.x equals 5, yeah? And A is a structure, X is a member in the structure, and X is a bit field member, and 5 is your value that you provided yourself, then GDB represented the value 5 as an integer, as a full-size integer, right? Not just however many bytes the bit field holds. So on little endian systems, actually the least significant bits of that thing were then transferred. But on big endian systems, the wrong bits were transferred, and usually you got zeros there. Then register pieces on big endian targets were completely broken. They only worked in very special cases where everything was byte aligned and very simple. In all other cases, they were just broken. I mean, there were so many bugs I cannot even list them here. This logic was completely redone. And then another interesting thing is that obviously the compiler has not emitted offsets for bit pieces very often, because they were always ignored by GDB up to last summer. And the offset was just replaced by 0, silently. For whatever reason, I mean, yeah, it was just ignored. It's now respected, but I'm not sure whether the location is actually done correctly, the placement, right, which I talked about before, because I really don't know what is to be expected there. Then there was also a bit and byte offset mismatch and a parameter to read value memory. So this is part of respecting the piece offset. As soon as we respect the offset, actually passing it to an internal GDB function correctly is also something that was done wrongly before. Okay, so this is just an overview of the bugs that have been fixed. There are still some open bugs that I know of, at least, and there are probably much more. So first of all, pieces from vector registers on IBM Z, at least, and maybe on other platforms as well, are taken from the wrong side. They are taken from the whatever the least significant bits of a vector registers would be. I mean, they're at least taken from the higher addressed bits, right? The highest addressed bits. And that's not compliant with the ABI because the hardware doesn't like that, right? The hardware allocates floating point sub-objects on the left-hand side, so on the lower addressed bits, in the lower addressed bits, so in the most significant bits, basically. And another problem that is related, not exactly part of the dwarf piece thing, but related, is that we have no support for unwinding parts of a register, which is needed now that some registers are can maybe not be unwound completely. A vector register on Z, for example, cannot be unwound completely, but a floating point portion in it can maybe be unwound. So the other 64 bits are undefined, and that cannot be expressed right now. The only thing that can be expressed is that everything is undefined, and that's bad. So, and another thing is that something that may complicate our logic quite significantly in the future is if we ever want to support the NDNET attribute of dwarf. That is not supported by GDB at all right now. It's also not specific to pieces, it's just a general thing, right? We do not support that at all.
Is that ever emitted?
I don't know. I would expect that Ada could emit it, for example.
Doesn't have to be for C as well. Power.
Yeah. So I would expect it to be emitted. I haven't checked.
It doesn't emit it.
Yeah, it's not respected right now. Yeah, so that's all I have. Any questions?
I have some questions.
Yeah.
Did you file like dwarf bugs?
Yeah.
Okay.
Yeah, they were rejected. I filed 2 of them. They were both rejected.
Okay. Like rejected with a reason?
Yeah, I can send you the reason.
I mean, I don't know. Like, what about? I'm curious about other tool chain. Like, does LLVM and LLDB have these same problems, different problems? I agree with GCC, and then you said GCC sometimes didn't agree with itself, which I'm super curious about.
Yeah, in the case of vector registers on Z right now, that's where GCC doesn't agree with itself. It actually emits bit pieces for things that should be left aligned with the same offset as things that should be right aligned. So it's indistinguishable by GDB what GCC meant by that. It's buggy.
What about like LLDB or LLVM?
LLDB, as far as I have seen so far, the last time I looked at least, LLDB just was LLDB's logic was just inspired by GDB's logic, so and GCC's. So I think we are ahead of this right now with GDB. I think I'm not sure. Is anybody from LLDB here, or does anybody know more about this? I don't know.
So then, what do the compiler guys say about this?
I've tried to get an answer from them. They have not responded. Well, it's not completely true. I mean, I talked with Ulrich, and Ulrich has the same question marks in his head as I have, but that doesn't help us very much further. I wanted to get an answer from Jakub, for example. He didn't respond. I don't know why. Probably because he thought that it's something that he needs to devote more time on, and he didn't have a chance to do so. I don't know.
Or is this something that there are several references to the ABI? The standard refers to the ABI thing.
Yeah.
The ABS, yes. is this something that the compiler guys and the debugger guys could sit and say, well, this is what GCC does mostly.
Yeah.
So this is what we'll say we'll do, and we can write it in the API somehow, or whatever addendum document for power.
That might be, yeah, might be possible.
And
Apart from the fact that it's currently broken, but
yeah,
we have to fix it somehow. Yeah.
fix it somehow, and then you say, this is it,
Right. Yeah.
and you solve it that way.
Yeah. Unfortunately, I think at the moment I'm the only one working on this. So I would have to make the patch for the compiler. To fix it.
It sounds like the standard is vague because nobody knows how the different architectures actually do these things. Maybe it's completely different for each architecture.
Yeah. Well, some things could probably be expressed in an architecture-independent way still, right? So, but I really think that at the time when the DWARF standard, or at least these parts of the DWARF standard were created, not all of the variants were known or were taken into account, right? Some things didn't even exist at that time, like vector registers just started to come into existence, but yeah. So that's my feeling, that these variants were not really taken into account.
So, why didn't you open an issue ticket at DWARF?
I did.
Yeah?
Yeah.
And there was no discussion?
Yes, it was. There was discussion. They were rejected.
Ah, okay.
Yeah. There was a lot of discussion. I didn't come through. I don't know why. I tried everything I could.
The issues are actually on the DWARF standards. And they're mostly rejected with quality of implementation.
Yeah.
Sorry.
Mm-hmm.
What you're saying is you'll end up with a producer check in the debugger, and you have to have the debugger agree with the compiler.
Yeah, maybe.
That's what it means, quality of implementation. Yeah, but that's the name.
That's the name.
What the hell do you have a standard for?
Yeah.
Well, not for quality.
Actually, maybe you could try a different approach. That's what I tried a few times. I wrote a patch for, actually I was working at debugging for subsystem of LLVM and CLang, and I created some patches, and the situation was not clearly described in DWARF standard.
Mm-hmm.
So I created a code review issue at Fabricator at LLVM, and included some debugging for subsystem maintainers in there, and all of them are actually members of DWARF standard committee.
Mm-hmm.
And after discussion on the code review, they asked me to put an issue to DWARF STD list, and after that it was accepted. So first show them the code, show them why it should be implemented and why it is why the standard is not very clear about that, and then they will point you at the DWARF STD. So just try to take it from the other end.
Yeah.
I really agree. I think first the tools have to be somehow. They're in the field already producing things. When you have the tools agreeing, then you can come to the standard saying,
Right.
this is what makes sense. It's implemented.
Yeah, I tried it that way.
Yes, but
I mean,
his problem is that he doesn't have. He would.
nobody talks to me. That's my problem, right? Jakub is basically the GCC guy for DWARF. He doesn't talk to me. So whom should I talk to?
To Jakub.
Jason.
I believe Jason is also on the committee.
Yeah.
So
Yeah, but they're both very
Yeah.
they're always busy.
Yeah. Ping them on.
Yeah, it's maybe not important enough. I don't know, but
Maybe,
Or it's too difficult.
maybe they're expecting the Power and S390 guys important things to step in and get involved in the discussion.
Where?
I mean, it's not clear what least significant bit means,
Yeah,
right? And
right.
maybe they're expecting that's vague because they're expecting the ABI to say least significant bit for this architecture means that.
Yeah, but no ABI does that. Not even the x86 one. I mean, why would it? Right?
Maybe it should.
Yeah, but even then, it's not what the compiler does right now, and it would also be bad. So we don't want that. It's not efficient, right? I mean, then we would have a lot of binaries that are broken right now if we would change it like that. We could then not express left-aligned pieces in vector registers with byte pieces, but we would have to use bit pieces. But we cannot use bit pieces because we don't know the offset.
So, what was
Understand the problem?
Actually,
I thought that the binaries are already broken. So
Yeah,
you
but
just have to say they're broken.
the problem is if you have a vector register and you want to take a piece from the left side, right? This is not the least significant side on big Endian systems. The least significant is right. Okay, so right now the binaries just emit dwarf piece operations that expect to align on the left. And that is also what is best for this architecture in this case, right? Because if we wouldn't have that option, then we would have to express it as a bit piece from the right, from the least significant bit, but then we would have to provide an offset. But which offset do we provide? If we provide 64 as offset, then it works for the vector register, but it doesn't work on old platforms that don't have vector registers. Because the same register number has been reused. It has just grown, right? It has grown on the right-hand side. Okay, so that's a special. So I think what we want is to preserve the current behavior and make the dwarf standard adopt to it.
how can the dwarf standard be precise enough, in general enough?
I've made a proposal. We can talk about that offline.
I read enough about this, I can read there's a proposal right now.
Okay, I guess we need to. So thank you.
Thank you.